So, in this lecture we will just continue our previous lecture about the fixed speed wind turbine generators. If you could see this block diagram of the fixed speed wind turbine generator, here we have the wind turbine and we have gearbox and we have the speed control mechanism and the synchronous generator. And with this arrangement we can achieve the electrical output from the generator. But however, here the power electronics interfacing devices are not present. So, because here it is a fixed mode type of wind generation system, and of course, we have this speed control mechanism. With help of the sensors we can sense the speed of the generator, and the speed can be sent to our wind turbines structure, where we can control the speed, I mean the pitch angle of the turbine, and so that we can maintain the synchronous generator speed constant. And what are the disadvantages of this type of wind generating system? The first one is the fixed speed systems may suffer excessive mechanical stresses. That is the first disadvantage. And second one, it absorbs the gusty wind forces, and this results in high torque, high stresses and excessive wear and tear. So, this is very important that it has the excessive wear and tear, so the maintenance cost increases. And the gearbox, basically this stress and the wear and tear mechanism basically is on the gearbox. So, that is why the maintenance cost increases here. And reducing the service life also, due to this wear and tear concept, the service line of the equipment also reduces. So, these are the disadvantages of the fixed speed wind turbine system. After that there is a change basically from the fixed generation systems, we have moved to the variable speed wind turbine generators. Why this variable speed wind turbine is necessary? As you already we have seen that during the fixed generating mode we have basically different types of disadvantages. We have like wear and tear, and stress is also there on the turbine section. So, to overcome those disadvantages, we have the variable speed wind turbine generating systems. And what are the first advantage of this particular system? It will just cope with stormy weather conditions. As all of us know that the wind system is very intermittent in nature. The wind speed, the wind velocity can vary from 2 meter per seconds to 16 or 22 meter per seconds throughout the day. So, in that case, if the wind speed varies, so accordingly our system should cope, and then only our system is going to be called as robust or stable system. That is why we have this variable speed generator. That system is ready, now it is also in operation, and it can cope, it can assist us during the stormy wind conditions. And second one, that we have the electronic control system is present here. In case of fixed mode of operation, as I said, as I mentioned that we do not have the electronic interfaces, but however, in case of this variable speed wind system we have this electronic control systems. The electronic interfaces are basically present, and this system, this electronic control system will keep the generator's output frequency constant during the fluctuating wind conditions. Basically what happens when the wind system, if this is our wind generator or wind generating system, it is connected to the grid. Now, this is the basically the point as known as PCC, just like our solar system. PCC means the point of common coupling, the where this wind generating system is connected to the grid system. Now, we have to maintain the frequency and voltage of this particular PCC at constant, at the desirable level or at the nominal values. So, for that purpose this electronic control systems help to maintain this frequency and voltage at the desired level or at the desired values. This is how this variable synchronous generator based wind systems looks like. Here we have the variable speed fixed pitch blades, or we have this wind turbine section, and after that we have the gearbox, and further we have this synchronous speed variable speed generator, and after this is the extra part which is added here. This is the electronic converters. The first part of this electronic converter is this rectifier which converts AC to DC, and the second part of this electronic interface is this, it converts, that is our inverter section which converts the DC to AC power. Now, we have the DC link. With help of this DC link, the two converters basically connected with each other, and of course, during the operation this DC link voltage should be maintained at the rated values to maintain the push the power from one side to other side. Now, if you could see in this particular block diagram, the electronic converters are basically connected between our grid system. This is our grid system, this is our grid system where this wind energy system is connected, and we have here the whole variable speed. Here actually this is kind of large scale wind power inline frequency conversion system. This is a very important term. Why it is inline? Because the total amount of power which is generated by this synchronous generator is fed to the grid system through the frequency converter or this powertronic converters. The 100% power is basically flowing through this converter section and it is reaching to our grid section. That is what inline frequency control type system. This is how it operates. You can see here this rotor and turbine can be run at a variable speed. This rotor and turbine of the mechanical part of the wind system, it can run at a variable speed, and to produce a varying frequency output from the generator synchronized with the drive shaft rotation speed. This basically the output, to have this a varying frequency output, basically the generator is synchronized with the shaft rotation speed. The grid side converter, if you could see here, we have like inverter here, we have rectifier here, and this grid side inverter, it helps in providing the reactive power to the grid, and also it controls the power factor and voltage of the grid system. These are the basically the functions of the grid side inverter. The first one is it controls, basically it provides the reactive power to the grid, and also it controls the power factor. This is the power factor theta and the voltage of the grid system. Because we in the powertronics devices we have thyristors or IGBTs. So, by basically the controlling the firing angle of these devices, so we can control these quantities, voltage or power factor. Now, by varying this, that is what I just said, that varying this fire angle of this thyristor switching in the inverter, and thus the phase of the output current with respect to the voltage also can be controlled. Basically, by controlling the firing angle, we can control the phase angle between the current and voltage of the grid side, that is at the PCC basically, where this wind system and the grid together they are connected. And third one is basically the doubly fed induction generator DFIG. In the previous model, what was the major demerit? The major demerit is that the cost of the electronic interfaces, the cost of the electronic devices are quite high, it is large, because this electronic devices basically they will see the 100% power which is basically flowing from the wind system to the grid system. But here in case of DFIG it is little different. What is the difference? We will see that. First of all, what are the components of this DFIG? Let us see. The first one here is the wind turbine, which is the mechanical part. Again also we have the gearbox, and next we have doubly fed induction generator. Here we are not using synchronous generator, we are using induction generator, which is called as doubly fed. Why it is called doubly fed? Because it has the stator, this is our stator, and this is the green one is our rotor. Now, both this stator and rotor, either they are going to push power to the grid, or they can get the power from the grid, or only the stator will push power to the grid and the rotor will receive the power from the grid side, or vice versa. The point is, it is a bidirectional flow of power. The power will be fed to the stator rotor, or it can just import or export the power from the grid. So, that is why it is a doubly fed induction generator. We will discuss more about what are the conditions as far as the operation of this particular generator is concerned. Now, if you see here, this is our stator power, which is denoted by PS, and this is our rotor power, which is denoted by PR. And this is the green portion I have just shown here. This is a electronic interface system, and here we have this machine side converter, and this is a grid side converter. Sometimes also we call it rotor side converter, and this is also grid side converter. Why it is this machine side converter is known as rotor side converter? Because the input to this converter is from the rotor, not from the stator. That is why sometimes it is called as rotor side converter, and as this particular converter is connected to the grid to this side, so that is why this is called as the grid side converter. And finally, this PS plus PR, the total power is fed to the grid. Basically, this stator power and rotor power are added, and the total power P total is equal to PS plus PR is fed to the grid. Now, here the first advantage is this electronic device cost is less, because we are just pushing 30% of the power, 30% of the total power is pushed through this electronic device, because we are not pushing the total PS plus PR, we are just supplying PR amount of power through this electronic device, and it is just reaching to our transformer, 3-phase transformer, and then it is just going to the grid side. And as a result, so cost of this electronic interfacing devices is basically reducing. And rest is, if you will see here, we have also different possibilities by just varying this firing angle of the converters, maybe of this rotor side converter, or it may be the grid side converter. We can always control the frequency and voltage at the PCC, the point where this wind system is connected and the grid is connected. That is our desire. I mean, we need this basically. Without the fixed voltage and frequency, we cannot connect the basically the wind system to the PCC, the grid system, because finally we have to supply a very steady, I mean the power quality, improved power quality best supply to the customers or to the load. So, that is why this voltage and frequency should be maintained fixed at the PCC, and that is why this DFIG is the best option. And also we have this additional control option, where this control system can also supply the information of the speed and as well as other factor. So, we can control the pitch angle of this wind turbine or blades, and also we have control system which are dedicated for this converters, rotor side converter as well as for the grid side converter. And these are some of the operational parts already I have just discussed. The typical speed control range is 30% of this synchronous speed, and the greater the speed control range, it may be necessary to implement separate pitch control and turbines rotor winds. So, these are the points already we have discussed in that particular part. And this is how this domestic wind turbine structure. We have variable speed fixed pitch blades, and we have asynchronous generator, means it is a variable speed, the frequency, I mean the frequency, the speed of the generator is not fixed, that is it is asynchronous. It is not rotating asynchronous speed, but the speed is basically varying. Asynchronous generator, we have this rectifier, and from the rectifier we have this voltage will go to the voltage regulator, and we have the DC control unit, because the output of this generator is AC, and this AC is converted to DC with help of our DC rectifier, and this voltage regulator will supply the DC output to the DC control unit, and it will just go to the inverter section, which will again convert to AC. Or what will happen if we need some DC output or some loads are DC. So, directly from here we can supply the DC power to those loads, and if we have some AC power, AC based loads. So, from the output of this inverter we can supply the AC power. Again we could have some battery arrangement, because if you want to store the energy at certain point of time, if we have surplus power, then of course we can store the power using a battery system, and this is a battery. So, the output of DC control unit go to the battery, and again during the requirement period, then this battery will supply the DC power, basically the DC, to the inverter section, and again it will go to the AC loads. So, this is the domestic wind turbine structure. And just here I just want to say, already we have discussed about this variable speed DFIG system. We have this rotor side converter, we have grid side converter, and in case of this rotor side converter, we have the control strategy. This control strategy basically takes the input as the reactive power as input, and this electromechanical torque is also another input, because we have to control the speed, the rotor speed. So, for that we need this Q and TEM, the electromechanical torque, and here in case of your grid side converter, we have this input as a grid side our reactive power, and this VDC. VDC is the DC link voltage, and we have MPPT. This MPPT is basically maximum power point tracking system, and it tries always to track the maximum speed of this wind system. So, or indirectly we can say in this manner that the wind generator should operate at the maximum torque to harness the maximum power. Either we have to basically maintain the pitch angle of the blade in such a manner that it should just harness the maximum speed of the wind, and further this maximum speed of the wind system, it will convert the kinetic energy to mechanical energy. Again that particular mechanical energy will be converted to electrical energy. So, that means to achieve the maximum power or maximum torque, this MPPT algorithms are basically dedicated. Just like our solar system, we have also MPPT system, MPPT technology, and there what we do basically to achieve the maximum power, that is PM from the solar panel. So, we control this mechanism using the MPPT technology, that is maximum power point tracking system. And here if you see, the control strategy has basically this control of extraction of maximum wind power. The first control mechanism that is used, that is the MPPT, and method is stands for maximum power point tracking. So, the aim of this particular control strategy is to extract maximum wind power, that is our aim using this MPPT technology. Now, second one is the control of RSC, that is a rotor side converter, by controlling the electromagnetic torque and reactive power of stator of DFIG. What is the aim of this second controller side, that is the rotor side converter? By controlling the electromagnetic torque and reactive power of the stator of the machine. And the third one is the control of GSC, that is a grid side converter, by controlling the DC bus voltage. This is the DC bus voltage, this one is our VDC. We have to control this. If our DC voltage, DC link voltage is not maintained properly, so the power conversion from the DC side to AC side is not proper. So, always we have to maintain the DC link voltage at proper value, at its rated value. And that is why by controlling this DC bus voltage, active and reactive power exchanged basically within the network, we have to maintain at proper value. So, these are different control strategies, just I have shown 3 here, MPPT, and this is the control for this rotor side converter, this is the control system for the grid side converter. In detail we will just provide references, you can go through the control strategy of this MPPT and of the rotor side converter and the stator side converter. So, these are some summary of operation of this DFIG system. The first one is, if our electromagnetic torque is greater than 0 and the slip is less than 0, that means it is negative, and our this Wm is greater than Ws. This Wm is the mechanical speed is greater than the synchronous speed, and here and this P mechanical, the mechanical power basically is greater than 0, that means the input to the rotor is higher, and that means it delivers mechanical power. The mechanical power is greater than 0 means it delivers mechanical power, because it is obvious, because in motoring mode the mechanical power is higher, the mechanical power is the output. And here this PS, the stator side power is greater than 0, that means it receives power via the stator. If it is greater than 0, that means it is receiving the power, it is receiving power from the grid. And similarly, this PR is also greater than 0, that means the machine receives the power via the rotor. So, in this case the machine receives this wind generator receives both stators and rotor receives power from the grid. If it is grid, this is our PS and this is our PR. So, both the stator and rotor receive power from the grid side, that means it is receiving the electrical power and delivering the mechanical power. So, these are the conditions for operating this DFIG in motoring mode. Now, second one is the generating mode. Here the slip is less than 0, that means the machine speed is greater than the synchronous speed. If the rotor is rotating more than synchronous speed, so it is called as super synchronous speed, the super synchronism, and at that condition the P mechanical is less than 0, that means it receives the mechanical power. So, mechanical power is, the machine is receiving the mechanical power, and at that moment this PS is less than 0 and PR is also less than 0. That means the machine is delivering the power to the grid in both the cases. If you could see here, it is just opposite, the wind system is delivering power to the grid, PS and PS, this is PS and this is PR. And this is how this generating mode happens. And the third one is again the generating mode, where we have this TEM is less than 0, and our, in this case it is sub synchronous speed. Sub synchronous speed means the speed is below the synchronous speed, the rotor speed is below the synchronous speed. So, that is known as sub synchronous speed. In this case also this P mechanical less than this 0, that means it receives the mechanical power. And what is the condition for this PS and PR? This PS is less than 0, that means it delivers power via stator, and however this PR is greater than 0, and that means it receives the power via the rotor. So, that is why it is called as doubly fed induction generator. The power can be extracted from the grid or it can be sent to the grid side. That is why it is doubly fed induction generator, and similarly the fourth one. Now, we will come to the wind power calculation section. Here we have this structure I have shown that the swept area AT of the wind turbine. Let us say the swept area of the wind turbine increases. Area A1 is basically less than A2 less than A3. This is our area A1, this is A2 and this is A3. And this is our wind speed, this is V1, Vt and V2. The swept area is nothing, the area where the wind is, the wind thrust is just fall or on the blades of the wind turbine, that is the thrust, I mean the swept area. Now, if you will see the kinetic energy of a wind is given as E. This E is equal to half of mv square, where this m is the air mass, that is in kg, and v is the velocity of the wind, that is in meter per second. That is our first equation, the kinetic energy which is present in our wind. Because we are interested to convert this kinetic energy to electrical energy, using different type of technology. So, this power in wind is how much? Now, you know this rate of change of energy is our power, that is dEt by dt. So, if you just take the derivative of first equation, so you will get half of v square dm by dt. Now, what is the mass flow rate at the swept area? This is a q, the mass flow is dm by dt, the mass is m. What is mass? Mass is basically rho a dx, volume into the air density. Rho is the air density, that is kg per meter cube, and x is the distance in meter, a is the wind swept area, just we have discussed in the previous slide, swept area A1, A2, A3, just I have shown here. So, this A is the wind swept area, and if you just put all together, so we will get this q as a flow rate, that is dm by dt, rate of change of mass flow, that is known as the q, and that will be rho a dx by dt. Now, if you just put again this velocity v is equal to dx by dt in equation number 3, then this q will be rho a v. Rho is the air density, a is basically the wind swept area, and v is the wind speed. Putting all together the equation 5 into, finally, the power in the wind system will get how much? Half rho a v cube. This is a very important equation. If you will just analyze this equation, this power which is present in wind, it depends on three things. The first one is the rho, that is the air density, the second one is the swept area, and v is the wind velocity. So, these three things basically govern or control the power which is present in wind system. Basically, according to the Ben's law, that he said that 59.3% of the kinetic energy of the wind is basically converted to mechanical energy. That is only possible, that is the highest figure we can achieve. So, that is why what is this, keeping in mind this figure 59.3%, the maximum power efficiency coefficient, the output power by input power, the efficiency of the wind turbine, if you will tell, I can say in this manner, output by input ratio will be how much? That will be 0.59, and that is known as Cp max, that is known as the maximum power efficiency coefficient. If you will see in further derivation, we have given here the book, reference book, where the detailed derivation of this Cp is provided. If you will see further analysis, the Cp is a function of this tip speed ratio and the blade pitch angle and the turbine radius. So, that is why while we design this particular wind system, we are always careful for this what is that, this turbine ratio. So, if you will see, this is our turbine ratio. If you take a horizontal type of rotor structure or wind system. So, this is our turbine diameter and this is the radius, half of this d, that r is equal to capital D by 2. So, this Cp is dependent on this turbine radius, that is first, and second one is the blade pitch angle, that is basically the beta. This beta is shown here. if this is my plane of rotation and here is the blade and this is the axis of the blade and this is the wind speed, this is my wind speed. The angle between these two is basically the pitch angle, beta, blade pitch angle. It is the angle basically between the axis of the blade and the wind direction. Between these two, the blade pitch angle exists. And third one is the tip speed ratio, that is our lambda. This is basically R ohm by V. What is this R? This is the turbine radius, okay. And we have also here ohm, that is the turbine angular speed. In some books also it is written omega, angular, this turbine angular velocity, at what rate it is basically rotating. Now, if we will just put all together, so we can get this Cp expression, okay. So, this is the expression where this you can find that Cp is directly connected to this tip speed ratio and also this turbine radius and the blade pitch angle. So, these are the things they are dependent, and the C1 to C6 are constants. Now, this considering the Cp, the output power, this P naught can be represented as P naught is equal to half of Cp rho A V cube. If you see the previous expression here, this is the here we have not considered the Cp. If we will consider the Cp, the output power will be half of Cp rho A V cube, and every details are provided in this particular book. And this is how we will just see the wind power equation. The first one is this power extracted depends on the design factors. The first one is the swift area design and environmental factors like air density, that is rho, which is basically in general 1.22 kg per meter cube for sea level, and also it depends on the wind speed, cube of the wind speed, and some control factors like we have this rotor speed omega, or I have just noted here this ohm, and here the pitch angle theta, here we are denoted by this beta. Coming to this characteristics of wind power, it is like this. So, here the first point is the curtain speed. What is curtain speed? The curtain speed is that speed below which the wind turbine will not produce the power. It is the minimum speed. So, below which we cannot produce the power, the windmill cannot produce power, that speed is known as curtain speed. And second one is the rated speed. The rated speed is that speed at which the rated power of the turbine is produced. At that during that period, the rotor is basically safe and the machine is safe, the whole system is basically in stable mode. And what is the cutoff speed? It is here the cutoff speed. The cutoff speed is that speed beyond which the turbine is not allowed to deliver the power. So, we have to cut, we have to stop there, the machine should not operate beyond that speed. Basically it is in the range of 20, almost 20 to 23 meter per second, and the curtain speed it also varies depending upon the wind structure and wind state. So, it is here almost about 4 meter per second, 4.54, you can say here 4 meter per second. Now, this is the another characteristic which is basically between this power coefficient Cp and the tip speed ratio, and here it is by varying this beta. Already we have discussed this Cp equation here. If you could see, the Cp is dependent on this beta and also the lambda and this ohm. If we vary this beta, the pitch angle of the blade, then what will happen? The Cp will move in this direction. If you keep on increasing, so you see here the blue one is beta equal to 0 degree, and here the maximum beta is equal to 20 degree. So, for beta is equal to 20 degree, here is the Cp value, it is less, and if you just increase, I mean decrease this beta value to 0 degree, then the Cp will be maximum. Because why it happens like this? If you could see this explanation, I mean this particular equation, that beta is in the denominator side. If you increase the beta, the Cp value will decrease. If you decrease the beta value, then Cp will increase. Now, this is the power production curve like for generator side. This is the generator torque versus the generator speed. So, we have discussed that in this curve the maximum torque point always we have to achieve, because at the maximum torque point we can get maximum output power from the generator. This particular characteristic is a family of curves by varying this by increasing the wind speed. This is the first curve for when the wind speed is 2 meter per second, and this is for 4 meter per second, and so on. If you increase the wind speed, so obviously our maximum torque point also will increase, and of course we could not move beyond our rated torque. So, this is here the rated torque. So, that means this MPPT algorithm helps in achieving this particular maximum torque in the wind system. And these are some of the generator cut-in speed and speed limit and shutdown speed. As already we have discussed for the wind system, wind turbine system, for the generator also we follow that. Before, I mean below certain speed, the generator may not generate or it may not operate, and when it will just cross certain point, then it will, this point is known as cut-in speed, and above that it will just go and reach the speed limit, and this is our rated speed, and after certain period it will just go for the shutdown torque or shutdown point. So, just like our wind system. This is one more picture just I want to discuss that if you just have a rectifier and inverter system of a permanent magnet synchronous generator type. This is also fourth type machine, basically we also use in the wind system along with the DFIG, double fed induction generator, and this machine is also, this is not designed for very large scale wind farms, but in large scale wind farm we prefer the variable machines just like DFIG, and this is also very robust, and we also prefer in to some extent this PMSG. And these are some of the papers you can follow where every detail, all the mathematical modeling of the inverters, converters are provided, and from there actually we have taken this particular picture, and here I just want to say this VDC versus IDC curve, that if you just increase the similar manner for the DFIG we have discussed, if you increase the wind speed, then this IDC also will increase, and similarly VDC square versus this IDC curve looks like as the similar pattern we got for the DFIG machine here. Now, so in this particular wind system we have discussed about the different operating principle of the wind system, its advantages, its disadvantages, and then further we have discussed the constructional features of the wind system, and again we have discussed like fixed mode of generating system, that is a synchronous machine based wind system, and then we have discussed the double fed induction generator where we have advantages like 70% of the stator power basically pushed through the line, and 30% of the power is basically delivered through the powertronic inverter to the grid system, and there we can maintain the frequency of the PCC bus, maybe voltage also, and voltage frequency both together we can maintain at the fixed value according to our desired requirement. And further again we have discussed the wind power content, that is our P, which basically depends on the Cp, the rho, and the area of shift area, and also the volume of the wind speed. And finally also we have discussed different characteristics both for the wind turbine as well as the generators. So, thank you so much.